Okay, then welcome now to this second session here in the morning. I'm Florian Brüning. I'm a postdoc here in Alex Group and also co-organizer of the workshop, so you can also address me with any question during these next days. And yeah, and I'll be chairing this session. So our first speaker is Yury Lysogorskiy. Yury obtained his PhD at the Kazan Federal University in Russia, then moved as a postdoc to Ralf Traut's group at Bochum University in 2017, where he was one of the key persons behind the atomic cluster expansion ACE, which is really foundation many of the current models. And yeah, now he is a research group leader at ICAMS, the Interdisciplinary Center for Advanced Material Simulations in Bochum. And yeah, I think presenting to us the latest advances of the ACE model in architecture.
Thank you very much for the nice introduction. First of all, I would like to thank the organizer for inviting me here. And today I would like to make some overview of ACE and GRACE ecosystem of the models that we do develop at ICAMS, and in the context of foundational universal general purpose machine learning potentials. So this is our IMS department at ICAMS, so the people that made this progress possible, and I would like to also thanks all of them for the contribution. And let's move first to the simple question: what if you take 10,000 atoms from the whole periodic table, throw it in a box, and let it cook? So just out of the curiosity, we did this experiment with one of the foundational models that we recently developed, and as a result of that, we take some sandwich, obtain some sandwich of the atoms, which we call Mendeleev array because it contains 94 elements. And if you do some post-processing and analysis, decompose it by graph clustering analysis of this complex piece of bulk of materials, we can easily decompose it into some chemistry sensible compounds. For example, refractory that was condensed first, then actinide iron fluorides, and so on and so on. But that's not the main goal to simulate this material. This is just a demonstration of capability of foundational models that can capture a wide range of chemistry. So that's why first we go to the graph atomic cluster expansion and atomic cluster expansion that was mentioned by Florian already. I would not do a big mathematical introduction to that. I just try to limit myself to the couple of slides because already a lot was said this morning about the different way of modeling, machine learning modeling of atomic interactions. And in the context of atomic cluster expansion, graph atomic cluster expansion, we, as usual, consider local neighborhood. So this kind of localization allows us to get rid of the non-localities that we may have in the pure quantum system. So that's the first approximation that we usually do for machine learning interatomic potentials. And in order to kind of have the full description of this interaction, we have to consider multiplets of atoms at the same time, like pairs, 3-atom, 4-atom body clusters, and so on and so on. And if we want to make it more, that's fine. So if we want to consider it explicitly, we need to consider all possible combinations of these doublets, triplets, quadruplets of atoms, but it became computationally infeasible. So the trick that we do using atomic cluster expansion is so-called density trick, whereas we swap the order of summation over the descriptors versus summation of the neighbors. So the first we sum over neighbors, and then we get work done with the descriptor space. So this allows us to get rid of this polynomial complexity of the multiple many-body subclusters and open the route towards the efficient from one hand side, but also fundamental, because formally this type of models give you the formally complete basis set. One can show it by, and it was shown already in this multiple works, starting by Ralph, Christoph Ortner, Dusson, and so on and so on. So atomic cluster expansion is formally complete basis set if we consider local atoms within some interaction range. We already had a lot this morning about the message passing, which is a way forward to increase the accuracy of this description of atomic system. And this message passing from other point of view could be considered as extension of this basis set. So instead of a local atom, we can consider, let's say, 2 hops, 3 hops, and so on. You get 2, 3, 4, 5 message passing layers. But we can formalize it through the theory which we call graph atomic cluster expansion. So, which is just another interpretation of what we can do in this message passing. Of course, after this is formalized, we can build, or we can kind of prove that it's also give you the formally complete basis set and the semi-local interaction. And we can construct the methods that allow efficiently evaluate atomic interactions within certain neighborhood of the central atoms, which is achieved by the several rounds of constructing this basic local ACE. So we start from the, let's say, furthest layer, construct this ACE descriptors of local atomic environments, decorate which will be decorated like this, and then we repeat the procedure and convolute it more. So we can repeat it from 1 to many times, so we'll have multiple rounds of message passing, and that's in principle the theory that from other point of view could be considered as a message passing. All right, so as I mentioned already, we do develop the whole ecosystem of ACE and GRACE models, so that's our series of ACE models. So we started with PACE, performant atomic cluster expansions, that we developed in 2020 and 21, and the pacemaker is a tool that we kind of provide for out-of-the-box parameterization of potentials. And this series of GRACE models, starting from, let's say, close to linear one, GRACE 1 layer, 2 layer, and you could imagine 3 to 3 and 4 layers even possible. So just some details about this series of models. So from PACE and GRACE, we do use so-called linear radial basis functions that describe the local atomic interaction. And we use MLIPs on some non-linearities for the more complex models. According to this theory of local, which we call star graph, and semi-local, which we call tree graph type of interactions, we can also split this 1 layer, efficiently 1 layer, and more than 1 layer interactions. Because we would like to speak about foundational models, of course, we do not want to have the limitation in the number of supported species. So this GRACE type of models through the tensor decomposition of expansion coefficients could be reduced to the case when we have just chemical embedding and no limit in the number of species. So the standard. We do support both C++, TensorFlow, and Cocos implementation. So parallelization is also an important aspect of simulations if we want to simulate large scale or long time. So we also do support now across all multiple layers models as well. And some other features, for example, chunking to allow out-of-memory footprint if you have just 1 GPU, but you want to simulate million atoms. Of course, you can do it now with these models without going outside of the memory. And uncertainty indications that I will dedicate some part of my talk as well, because it's necessary aspect of the model. We want to know where our model interpolate or extrapolate to have kind of some reliability signal. All right, so for foundational models, we started with what is nowadays considered the first exercise in this foundational model in material science. So I also have to mention that our focus mostly on material science, not chemical and molecule one, but mostly material science, condensed matter. So that's why we focus on OMA datasets from Meta and Materials Project and Alexandria one. So using these datasets, the big one is 110 million calculations with some further one which is around 10 million calculations. We have some training pipelines starting from the pre-training on this big OMAT model and fine-tuning it for this set of data sets that are usually necessary if you want to participate in so-called mud-based discovery competition. So we did that, and so this screenshot was taken a few days ago. Once they introduced the MD test in this mud-based discovery, and here you can see that if we consider the 2 degrees of freedom, so this combined performance score CPS and AC MD speed, so it's just a Python evaluation of those. There is some Pareto front that is formed by a set of models. So Grace models really sits on the Pareto, also the Pareto front in these two aspects. So they are accurate enough and also computationally performed. But what if you want to go for more extreme cases and to simulate systems like this Mendeleev alloy that we have seen on the first slide? For that, we need to really focus on sampling of this sampling strategies of these training data sets. For this purpose, we, in collaboration with Danny Peretz, we generated so-called SMAX data sets that contains roughly 1.7 million DFT calculations only, computed with PBE. But the sampling strategy, contrary to the OMAT data set, was different. So it was so-called entropy maximization in the feature space, and in chemistry descriptor space. So we have very diverse chemical and configurational coverage. So on this PCA decomposition of all different data sets, you can see that in SMAX you have quite heavy tail coverage compared to, for example, OMAT, Alloy, MATPES, and so on and so on. So this data set, SMAX, really kind of, despite its small size, it can be really kind of the way of regularizer for very extreme case of simulations with rich chemistry and conditions. So what we also did, we combined this SMAX and OMAT data sets by exclusion of +U configurations, +U calculation from this OMAT, because we know they do some discontinuity in the potential energy surface. So we try to clean it from that, and we get a new set of models which we call SMAX OMAT models. So now they also cover quite wide configurational space without +U correction. So in some cases, this absence of +U correction makes things smoother for some simulations. For example, if we take the nickel and nickel surface with a nickel oxygen top layer and try to exfoliate it, we tried with different models, and that's how we actually found this test case. Grace, OMAT, and OR models show some drastic drop because once you move nickel from oxygen, it's due to this discontinuity, it's swap internal state from +U to no U, which brings to the things like that, which means just discontinuity. So it's problem not of the model, it's problem of the data set, because other models, most of them struggle from the same deficiency. Contrary to that, this SMAX model or SMAX data set perfectly fine without any fine-tuning define this deflation trajectory. So you can see +U is not always correct. And with this SMAX model, we also did some for fun simulations, what we call lava simulation. We just take top 9 elements from the abundance list on the Earth's crust, put it together, and cook it from 5,000 K down to room temperature. And what we observe, some formation of course, glass, silica glass, alkali metal glass, and some iron silicides, which not frequent things in the Earth's crust, but in the absence of oxygen, because we just take formally the typical average oxygen concentration may form there. Once we take this, we take some random subsets, like clusters from this, just to validate the model. So we randomly crop some cylinders out of this slab, we compute with DFT, and we get quite nice, like 100 milliliter angstrom. This is a quite low energy when you have oxygen, actually. And so we prove that models behaves correctly, even in these complex simulation conditions. All right, so, but how we can be at least a little bit sure that our simulations is going in the right direction without computing DFT after every iteration. So for that, we do have uncertainty indication developed recently, and So here I have to mention that even in original ACE and PACE models, where we have mildly nonlinear models, we do use so-called de-optimality or Maxwell approach to indicate uncertainty. By uncertainty here, we mean that we work with latent space. In some cases, just pure basis functions, ACE basis functions that formally complete. In Grace models, it will be some projected basis functions, so projected features from the basis functions. But we work with some latent representations. And the first generation of UQ, uncertainty quantification, uncertainty indication, was based on the so-called de-optimality that was used first time, for example, in moment and in the potential MTP by Alex Shapeyev. Deficiency of this approach is that this de-optimality it works mathematically perfectly fine when you have linear models, but what does it do? It just makes some rectangle, whatever, in the feature space with a maximum point sitting on the border of this rectangle. And of course, you can imagine a situation depicted on this cartoon, so it's not real projection comes later, that in your training data, you may have such a distribution of local atomic environments being projected into this latent space that forms some non-convex distributions, like these semicircles of isolated clusters. And of course, with the optimality method, that would not be captured, because even inside here, that will indicate it as reliable, which is not true. So to get rid of this deficiency, we do use so-called Gaussian mixture models in this latent feature space. So what we do, we construct, so this is achieved by single post-processing step once the model is fitted. Once model is fitted, we know this local representations, we can build the Gaussian distribution. So on top of this most common parts, through the K-means clustering aggregation and so on. And we may use this as some probabilistic model for the density of training data set in this latent feature space. So that's the cartoon. That's how it typically looks like. So here I try to explain with this red ellipses, you see the actual trained data distributions and from the training OMAT data set. Whereas with this violet purple things, this is a projection from SMAX data set. SMAX is totally out of distribution for OMAT. So it's a perfect test case for this extrapolation. As you can see, they visually in this PCA projection, you cannot see all 128 projections we do use, but even in these two projections, you see that they are quite extrapolating. So it allows us to kind of on the fly identify if this given current atomic environment that you do see in your simulation is in or out of this distribution. Another example of this UQ is so-called out of distribution indication. In this numerical experiment, we have two sets of models trained on OMAT in the first row and trained on this OMAT SMAX mix, so which has much larger coverage. And now we can test it both on OMAT and SMAX. So we have 2x2 experiment matrix. Of course, if it's tested on OMAT and trained on OMAT dataset, test on the same dataset, what we expect that all atoms will be indicated as reliable in domain. So that's what you see here, and typical error is something like 0.77 milliliter per angstrom for this Maya distribution. But if you now take this SMAX dataset, which is very diverse, you may have as large error as tens of EV per angstrom, so it's orders of magnitude larger. And in order to differentiate between them on the fly, we may use this uncertainty indication mechanism. And by selecting some threshold, you can see we can split it in two categories. Green is reliable interpolation, and red is non-reliable extrapolation mode. And so I have to notice this is a log scale on energy error, on force error, sorry. So it's not just slightly shifted, it's a drastic difference, because here mean absolute error for forces is roughly 130 milliliter per angstrom, and here it's 8.8, so order of magnitude larger. So long story short, this mechanism allows us to kind of identify if our model now try to evaluate never seen before atomic environments, which give you some not 100% accurate, but at least some useful signal about the reliability of your simulation. So now if we come back to our mid-delay follow simulation and we re-evaluate with this UQ model our trajectory, we can see that except of very first few steps when we have totally random configurations where we have above the threshold uncertainty indication, so the first random snapshot was extrapolative, quickly we reach the reliable region by this model because SMAX model was trained on the very extended training dataset. If I would evaluate the same using the OMAT model, then it will be like orders of magnitude worse. So this is really the kind of nice example of a difference in coverage of it. All right, so, but of course, having the foundational models from one hand side, which you can take and use it out of the box, and they have quite moderate quality for that. And second, having this uncertainty indication mechanism together give you already some useful combination which you can use in your typical simulations, but sometimes you want to have even more accuracy on your system of interest. So for that, we may consider two strategies which called fine-tuning and distillation of these models if you want to kind of move further. So first example is fine-tuning of this Grace Foundation model. In that case, we did use the OMAT model, so this big trained on these big data sets, but this test system is aluminum lithium binary alloy, which is very close to IID, so identical distribution, so it was actually quite easy to fine-tune. So two main points or two main lessons that we can extract from here is that even if you have roughly 1 to 5% of the original training data with the fine-tuning, you can already achieve the plateau on the error metrics that you would get if you do the full model parameterization. Also, if you compare to, for example, this red curve versus this green curve, red curve has the same model complexity but training from scratch, which is can demonstrate here the fact that if you fine-tune the model contrary to the training from scratch, you achieve this metrics very fast and you can be very data efficient. Combining with the uncertainty quantification mechanism from the previous topic, you can even optimize the selection of this necessary 5% of the data to achieve best coverage by smallest amount of the data. All right. So what if we go to the fine-tuning, but for the out of distribution type of data set, for example, this hydrogen combustion data set. And the problem is that out of the box on this data set, which was computed with omega B97 functional, we have very big systematic mismatch, first of all due to DFT mismatch, and secondly due to the configuration space sampling. And zero-shot MI was something like 700 mP/A, and this is allowed. So we have three possibilities, basically two possibilities to do this fine-tuning. So first one is so-called naive fine-tuning, when we, starting from the retrained model, we allow to optimize all the parameters of this model. With this approach, of course, you can achieve the lowest possible error, but there is some problem with this, so-called catastrophic forgetting. So foundational models, they remember a lot of general configuration space features and peculiarities, and if you start to fine-tune it on some small or non-small data set, this may be forgotten during this procedure. So in order to prevent this, we can apply some type of regularization. So one of the regularizations that we do use in our various models is a so-called frozen weights fine-tuning. Whenever we fix some part of our model, for example, radial functions, chemical embeddings, and so on, but allow to change the coefficients in front of the basis functions. So by this approach, so you can see on this Pareto front where we have, let's say, two target tasks. The new downstream task for this new data set, and so task which related to the original foundational model parameter data set. So if we have baseline model out of the box, foundational model, it has quite large downstream error, so we have systematic shift, but of course it has quite low original error in the original datasets. If we use the naive fine-tuning, which is shown here, we have already like 6 orders of magnitude error increasing in this original task because of the catastrophic forgetting. So by combining this fine-tuning of only part of the model of the back and keeping the backbone of the model fixed, we may find some configuration where we have at the same time low energy, so low error in the new task as well as low error in the old one. So which allow us to prevent this catastrophic forgetting. All right. The second point is, of course, this great foundational models in general, especially if you try to cover very large chemistry space, they must be computationally less efficient than the dedicated model. So because they have to capture the whole complexity of the foundational data sets. And of course, if you want to simulate longer and faster, you need some new models, which are called usually student model. So in this setup, in this approach, which is called model distillation or student-teacher approach, we may use some foundational models, for example, starting from here. So yeah, so forget me, maybe I first should explain what you can see on this plot. So in this case, we start from foundational Grace OMAT model, and that will be our teacher model, whereas our downstream task, dedicated one, will be so-called high entropy 25S dataset, which cover a lot configuration chemical space of high entropy alloys, including 25D block elements. So the point is that if we take out of the box foundational model, as usually, they have quite low error metrics on the original task, but they have some moderate errors on the new task. Especially here, because high entropy 25, as far as I remember, was non-magnetic DFT setup, whereas foundational models was spin polarized. So here we have once again systematic shift. So that explains the high error on this primary task. And we may have several routes of this fine-tuning and distillation. So we may start from this foundational model, and first we can do the fine-tuning toward another big Grace foundational models, but we can use this as a new teacher model and generate new training, so do the labeling using this model for new data set, so-called synthetic data set, that we may use to train new student models. So from this we can go to the, for example, through distillation towards this smaller type of models, which we call FS models. So this is a two-layer model. They're big and expensive. FS, they are smaller and less expensive. So we can swap the order. First we can do the distillation, then we can do fine-tuning. In principle, you will end up more or less in the same region. Even if you do not do this fine-tuning and distillation at all, you just take the final fast model and use your training target data set high entropy 25, you can have this bespoke model. So as you can see, we all end up in more or less on the same region of this plot. But once you have, we can follow another scenario. In this case, if you want your model, fast model, the student model, to cover not only this dedicated task, but also something around. For example, we added here also energy, so I think that was binary convex halves from these elements. You can use your fine-tuned teacher model to generate data beyond what you have in your DFT data set. So you can generate even more training data that covers something surrounding, not only your dedicated task. In that case, you can have even better what we call the extended distilled model that have, let's say, larger reliability range in this configuration chemical space. The same model complexity as here, but you gain in this axis as well by just generating more training data from your fine-tuned model. So, and of course, the main goal of these scenarios is to have a speed up. So, comparing this foundation versus extent one, we have something like 70x speed up on CPU and some other settings. Okay, the third example of fine-tuning and distillation is grace to pace. So that was done by our new group member, Christian Ritterhoff. In that case, he started with, so the system under investigation was amorphous carbon. This is very hard data, so it's not hard in terms of chemistry, but it's hard in terms of configuration of space, because we really have a lot of sampling of configurations of different densities and of carbons there. So if we take out of the box, in that case, Grace one-layer foundational model, you can see that prediction of this model is not so good. Especially you can see this bending down tails, which corresponds to absence of co-repulsion, for example, in some extreme case, at high densities, and so on and so on. The first step we can do is the fine-tuning of this model, so that's achieved here, and of course we can reconstruct the quite nice matching in energies and forces. So highlighting also the data sampling efficiency, as we discussed before, if we would parameterize the model from scratch, you require usually 5 to 10 times more data to achieve the same accuracy. So that's why fine-tuning is a good default starting point nowadays, once we have this foundational models. And second, once we have this fine-tuned foundational model, which we can consider as a teachable one, now we can do so, for example, which we call here active distillation. So we have another uncertainty indication mechanism in base models, so active, which based on the optimality, and through this several iterations, I think that was 5 or so iterations of this run MD, select uncertain configurations, and refit pace using your not DFT but your Grace model as well. After this several rounds of active distillation, we have some very fast pace models that can run on CPU, GPU, parallelized, and so on and so on. And we may run the same type of simulations as we had in the original work that we did, where we did generate this amorphous carbon data set. So that was, for example, one of the empirical tests was the formation of fullerene in some long time simulation, like 2.5 nanoseconds. So that's long for us, not for molecular chemists, probably. All right, so now I would like to speak a little bit about the computational performance, because we always keep it in mind once we develop our Pace and Grace models. In order to have possibility to use this accurate but moderate expensive, for example, Grace two-layer models, we need to be able to parallelize it over, for example, so-called domain decomposition method, which is a default one in LAMPS, where we have this implemented, and we now have this feature implemented, and in that case you can see how good, or let's say how not bad, is this strong scaling efficiency of this Grace two-layer parallelized model using the domain decomposition, and also through chunking, whereas we can consider system not as a one big bulk of atoms, but we can also internally split it into the subsystems and evaluate even on one GPU. So which release out of memory kind of cap for using this model. So you can see this a quasi-linear dependence. Of course, it's sublinear because it's not, we cannot have efficient parallelization, ideal parallelization on such type of models because of the feature communication, but it still allows us to do simulations like this. For example, in that case, we see something like imitation in aluminum, imitation of laser ablation. So in this region we have 5000 K hot initial temperature, and usually it's lead us to the formation of some bubbles, but then they disappears. So that was done with Grace two-layer model on 8 GPUs, and effective time was something like 4 microseconds per atom per step using this parallelization. So 161K atoms in this case. All right. We also worked a lot in recent years on the COCOS implementation. So COCOS is an open source performance portability library that is quite commonly used in labs as well. We did it for 1 and 2 layers models. So if you cannot see the slide, I will try to explain it here. So here you may see this typical timings in microsecond per atom per step. That's the typical numbers that we're fighting for. For 1, 2, So for one layer, two layers, medium to layer, large model, and that's the difference between Cocos and TensorFlow. So yeah, also I have to mention that now we switch the default precision for FP62, so single one, because we also realized that we do not lose a lot even in the metrics once we do it contrary to the FP64 originally. So on this right plot, you may see the number of atoms versus this computational time, and as evaluated in this Grace two-layer model Cocos implementation, and we may increase starting from 128 atoms, going up to like 32K, 64K, and after that we may switch to the so-called chunking. It means on one single GPU, in principle, you can go for several million of atoms. Of course, it will be proportionally expensive to that, linearly proportional. So it means that, as I mentioned before, this memory cap, out of memory error cap, can be released, and you can use one GPU to simulate large system by cost of time, of course. All right, so some Grace use cases. I have only a few of them, and the first one is not our work, but we just found it because it was citing our work, is glass electrolyte discovery using this Grace FS model, where it was fitted from scratch for 17 elements for different mixture of glasses, and active learning with the optimality as UQ mechanism was used. So second example was used by our colleague Sergei Starikov, so for this Grace two-layer OM model, when he studied defects in Laplace phases, binary phases. Because I mentioned we focus mostly on material science and condensed matter structural materials one, where he first evaluated on some dedicated system like copper to magnesium, chromium to titanium, and third one I don't remember, and compared to some DFT reference data. So this is a defect energy formation energies as evaluated by Grace versus some independent DFT values as before had, and you can see it's have very nice matching. All right, so, and the third showcase is was done by Grace one-layer model by Linus Erhardt for studying of copper-water interface and different roughening of this copper surface in contact with water. I would not go too much into details because it was just showcasing examples. Okay, and now the last section is a new foundational model. So I mentioned one layer and two layer. Of course, we can go further, like three-layer models that we released last week. And so there is a MAC-based discovery project that evaluates these foundational models on different tasks. So it's not only energy and forces Maya and RMSE, it's something more dedicated task. For example, the stability of or discovery of new materials, so convex hull stability. This is F1 metric. Also, it's so let's say for nonlinear interactions, so kappa, so thermal conductivity is RME metric here, and CPS and RMSD, so geometrical difference between model prediction versus DFT. So with this Grace layer or large model, we're able to achieve something quite close to the top performance. It's at a fourth place, actually, sorry, having only 42 million of parameters. And because we were working a lot on the computational performance, so we did rework the neighbor list and tensor coupling operations there. So with TensorFlow, it's allows us to achieve something like 64 microsecond per atom per step. So for two layer that was 20, but this is 3 times slower, but still it's quite performant, which if we come back to the original Pareto front that I showed at the beginning, bring us somewhere here. So this is a sweet spot of this Pareto front. Combining this CPS, combined performance score, on 3 independent tasks, geometry, phonons, and convex hulls. And what they do have on this MAC bench is ASC MD for some 17 systems as of now. All right, so maybe very quick I go through that. So other properties can be predicted with foundation. So not from foundation, but such type of equivariant models with Grace in that case. For example, tensorial properties, because we can extract not only the scalar, but some L1, L2 type of features, and for example, have Born effective charge model here, or we may incorporate charges as input to the model into this atomic base and get the charge trace model, so that's still work in progress. For example, incorporate magnetic degree of freedom, which also open route towards parameterizing non-collinear magnetism in systems. And even parameterize the multiscalar, in that case it's density of state, electronic density of state for some zirconium oxide. All right, and with that I'm on my conclusion outlook. So foundational models in general, or we may call them also general purpose machine learning force field, they quite a good default choice for start to study your system. So nowadays most of the machine learning and atomic potential foundational MLIPs, they converging in accuracy. We still can fight a little bit for this Pareto front and performance accuracy, computational performance and accuracy, but they seems to be converging, so more maybe accent should be shifted to the data generation and coverage, so we achieve it with the SMAX dataset. We also would like to highlight the importance of uncertainty indication mechanism. It must be default built-in, as I think for machine learning models to have at least some indication. It's not 100% guarantee that model is correctly predicting, but it's nice to have option. And computational efficiency always makes sense together with combining with fine-tuning and distillation of the strategies to extend the simulation length scales. And with that, I would like to thank you for attention, and I'm ready to answer your questions.
Thank you, Yury. Then, yeah, we come to questions. Please, Eugene.
I was wondering about your uncertainty quantification, because you said certainly, like if you go to an out of distribution set, you start to see the split of errors. But for the uncertainties, but how well does it correlate with actual error?
That's a good question. So, if I would say something like Spearman correlation 0.6, would that say something to you?
That's not bad.
Yeah. So typically we look at such kind of plots when we see the split into the two subclasses, and two criteria we do consider: if this in-distribution indication close to the training data distribution, and second, that it's not it has small amount of false negative. False negatives, what we try to finding for. And yeah, so that's our criteria, and correlation, as I mentioned, something like 0.6 with force errors.
Okay, so the uncertainty is slightly underestimating the error, but it's certainly it's well correlated. But I mean,
it's correlated, it's calibrated, but its discriminative ability is limited anyway. So
it's better at predicting if something is rather bad than good, but it cannot tell you, like, if you
it can predict if it's definitely out of distribution by construction, but sometimes it can mispredict if it's in distribution but has larger error due to some missing hidden parameters.
But it's not quite quantitative, like the uncertainty bar.
In that case, no, but of course we can build model based on some features. Internally, goal was not to train new model to make this kind of quantification. I think that was some error.
Yeah, there are actually many questions online, so maybe if you can answer those later, but I will read now one. So, question from Mikhail Rudenko. Thank you very much for the presentation. I have a question about the SMAX dataset. So, what were the maximum force and magnitudes and energies per atom in the dataset? In other words, how strongly distorted were the structures, and how much was the data distribution shifted towards highly distorted configurations?
Yeah, I cannot mention it out of my head, but I may refer you to this paper. I mean, this archive, for example, now with like more detailed definition of what we have in the. But I think it's larger. Probably PET-MAT data set has comparable coverage of force values.
Thank you.
More questions from the audience? Yeah, Eugene,
I don't want to take the time of anyone else, but I read actually the SMAX paper. There I saw the distribution, and one can see for ALMAP essentially the force distribution stops at the 100 TeV per angstrom, probably by design. But for SMAX, like that's still.
Yes.
What would be In what case would it be useful to have such high forces? I understand that if you have high pressure systems, you can benefit from high forces, but I thought like above 100, 150 eV per axiom.
Yeah. Sometimes we had requests, wait, my carbon at 1 terapascal doesn't work. Why? So that's what we need.
That's okay.
Yeah, so we have one more question from Amir Mahdi Zardoshti. So how do you determine the threshold for classifying a sample as out of distribution? Is it chosen empirically on
Yes,
theoretical basis for this?
It's 3 passover data set, and the last pass is calibration, where we select. We build something like what is called Mahalanobis distance, which is range from 0 to 100, which is what you usually see under this Gaussian exponents. And we use 95th percentile as this calibration boundary.
Thank you.
Okay, then I think we can move on to the next speaker. And we thank Yury again for this very insightful